Welcome everyone to the course. We're really happy to see you all here early this morning. For someone it's very late at night, and we appreciate you taking time joining the course. So today's lecture will be 90 minutes long. 1 hour will devote to the lecture itself, and half an hour for the questions that you have, and we will be answering those as we go as well. We hope that you find material very useful for your work. If you have any suggestions, again, please feel free to send us a request about that. My name is Julia Levdas. I'm a product manager now at Tesla Group, and I will help to kick off our first class. So there will be a lot of material covered during the class, and we will post a class recording of the course on the page, the same page as you use for the registrations. Recording will be available by the end of the week. So you will have an additional opportunity to review the course. All the lines are muted right now, so please submit your questions for a Q&A. The Q&A pod is the right bottom side of the screen. While submitting a question, please submit them to all panelists. That way we will all here will be able to help. We'll do our best to answer as many questions as we can today. Also, if we did manage to answer your question, you still have a few pending, please send them to openacc@nvidia.com. We have 2 instructors today. Both are amazing people and very knowledgeable trainers. Bob Cravella is a solution architect at NVIDIA, and he will be helping with the questions in the background, while Jeff Larkin will be presenting the lecture itself. So Jeff Larkin is our software engineer from the Developer Technology Group, where he works on porting and optimizing HPC applications. He is also closely involved with the development of both OpenACC and OpenMP specifications. So I guess that's it. Again, if you have any questions, please use the Q&A pod. We will be monitoring them and answering as we speak. And with that, I would like to get over to Jeff. Jeff, I think we're ready to start. Okay, Jeff.
Hello,
hey, Jeff,
can you hear me now?
Again.
All right.
Yes, we can hear you now. Go ahead.
All right, welcome everybody. The purpose of this course is to provide you with a basic introduction of OpenACC. No prior knowledge of OpenACC or even parallel programming is required. No knowledge GPU programming. We're going to kind of build up from square one for you. I do want to start off giving you kind of the course objective here so you know what you've signed up for. The objective here is that at the end of the course, we hope we've enabled you to accelerate your real science applications using OpenACC. It's one thing for us to provide you the test codes, which we are going to provide you some sample codes, and expect you to be able to accelerate those, but we really want, at the end of the day, for you to be able to go home, take the code that you care about and the science you care about, and use OpenACC to accelerate that science. This is a 3-week course. The first week is, of course, today. We're going to talk about analyzing your code, getting performance profiles, and how to begin parallelizing your code with OpenACC. Next week, we're going to follow on with that. We're going to take the same code that we work on this week and work on some optimization techniques. And then the last week is going through some of the more advanced features that you may or may not encounter as you're going along. So with that, the first week, and let me back up one step here to point out that this link down the bottom here, developer.nvidia.com/intro to OpenACC course 2016 is the page where you signed up for this course, and that is the page where both the videos and the slides will be made available to you. So if you can watch for them, we'll try to get them posted as quickly as possible. So with that, let's start off talking about analyze your code and parallelizing with OpenACC. And today we're going to talk about a 3-step process that we believe helps get your code running with OpenACC. And we're really going to feature 2 of those steps this week and 1 in the week that follows. First, today's objectives, we really want to make sure that you understand what OpenACC is and why you would want to use it. Next, we want to make sure that you understand some of the differences between CPUs and GPUs and how the hardware behaves differently. OpenACC, I want to point out, is not a GPU programming model. it is a parallel programming model, and you can take your OpenACC code and run it on a variety of platforms. But I work for NVIDIA, and you're here to learn about NVIDIA GPUs, so I do want to make sure you understand what CPUs are good for and what GPUs are good for, and the differences between them. We definitely want to make sure you understand how to obtain an application profile. That's always really the first step in getting going with your acceleration. And then lastly, make sure that you've experienced OpenACC directives a little bit and understand how to build and run your code. Now, we are providing you access to our Quick Labs system, which will allow you to do some self-paced, hands-on labs to experience all this for yourself. So I'll be showing you what to do, but you'll have some opportunities to run on some real GPUs using these test codes. So getting started, why would you choose OpenACC? What is OpenACC about? I think many of you I know are here because you're taking this as a part of a college course. There are many of you out there doing that. Some of you are probably here because you've heard buzz about OpenACC, and some of you may just be here just to find out what this is about. So let me talk about OpenACC for a moment. OpenACC is a programming model for really simplifying parallel programming. So it's designed so that you can use an advanced compiler and some hints that you insert into your code to help the compiler to build your code to run in parallel. So if we look in the top left box here, I have kind of a pseudocode, and you notice this green directive here, which is a compiler pragma in C, or in Fortran it would actually be a comment that has a special format. That tells the compiler, here is a region of code that I want to be run on my GPU. Now, I, the programmer, don't need to worry about how to restructure this code and distribute it on the GPU. The compiler is going to take care of that for me. So that really simplifies the getting started with using GPUs. Now, next, while it's simple, it's still very powerful. You can still get a lot of performance improvement from using OpenACC and running on the GPUs. We've highlighted two different codes here. The first one on the top right is a code that came to one of our GPU hackathons, I believe about a year ago, and they did MRI reconstructions. They had a lot of images that they needed to be able to process in parallel. Now, they came in with a code that was completely sequential. It just ran one image after another on the CPU, and after a few days of effort, we're able to see a huge speed up in their code. Now, of course, here they're comparing a single CPU core against a full GPU. So the actual speed up, if you compare against the CPU socket, would be less. But for them, that was their experience. They took a serial code and got it running on the GPU very fast in about 2 days worth of effort. Another code down the lower right here is a climate model called NICAM. And in this case, they only had to modify about 5% of their code, a fairly small amount of their code, and speed things up by a factor of about 7 or 8x. And this is actually a socket-to-socket comparison. So running on full CPU nodes versus CPU node, CPU plus GPU node, and you got about an 8x performance improvement. So with a very small amount of effort, they were able to get very large speedups. And the last thing OpenACC aims to be is very portable. Specifically, we want to make sure that the code you write will perform well anywhere that you try to run. So we'll revisit this graph in the bottom right in a few moments, but what it's meant to demonstrate for you is they could take, in this case, the Cloverleaf app, the same application, and by simply changing the compiler flags, not having to change the code at all, can run across CPU cores or across the GPU and achieve a good speed up. So we really believe OpenACC is a good answer for performance portability. Oops, my page down button is not working right. There we go. Now, one application that I'd like to highlight here is this Ellis Dalton application. Now, you probably have not heard of this application unless you happen to be a computational chemist. The Dalton application has been around for quite some time. It's been developed for many years. LS Dalton is a particular variant that improves the scalability, so it's a linear scaling Dalton. Now, this code is being developed at a university in Denmark, and specifically one of the PhD students there came to us because he really wanted to be able to run on the GPU. He had particular science he wanted to run that he believed the CPU would help him with, but he's a chemist first. And so for him, trying to learn a new programming model like CUDA just seemed like a daunting task. So instead, he came to us, he used OpenACC, And again, he went to one of our GPU hackathons, and in about a week's worth of effort and modifying a pretty small amount of the code, about 100 lines of code, you could see that he achieved very large speedups. And in this case, this is running on the Titan supercomputer, which is one of the largest computers in the world. And comparing against the full CPU node versus running on the GPU, you can see he's getting 8x and greater performance improvement. And what's important to him is he maintained one source code, no additional modifications, one source code to run both on the CPU and on the GPU. So what does OpenACC look like? If you're a C or C++ programmer, it comes in the form of compiler pragmas you may or may not have used before. If you're a Fortran programmer, it will come in the form of compiler directives, which are special comments. Throughout this course, we found that most of the people participating are interested in the C, so we'll be showing the C examples in the slides, but everything I say is applicable to the Fortran as well. I want to call out to you the three types of directives that are available to you. The one in the middle is an important one that I want to highlight first, and that's a pragma that initiates parallel execution. So in this case, I'm spawning parallelism on the GPU. Because GPUs and CPUs generally have two distinct memory spaces, we need to manage the fact that some data needs to be available on the CPU and some needs to be available on the GPU. And so the top directive there is directives for managing data movement. So instead of having to maintain, in this case, X, Y, and Z, and maintain two copies of them, one on the CPU and one on the GPU, we allow OpenACC to manage that for us, and it really simplifies the code a lot. And lastly, the bottom directive we see here is one for kind of optimizing the loop a little bit. So we have one loop, and we want to make sure that we tell the compiler what's the best way to optimize that loop. So those are the three types of directives that we'll be working with. Now, all of these can be added to your code incrementally, so you don't need to go spend 6 months in the woodshed completely rewriting your code, but you can incrementally work through your code and speed up the important parts. You can maintain a single source code that'll run on the GPU, it'll run on multi-core CPUs, it'll run in its original form sequentially, and it's interoperable with other programming models. So if you want to use accelerated math libraries, great. If you do have some existing CUDA code, we can interoperate that as well. And all of this means that it's completely performance portable. We really want this to be something that you can take from machine to machine and have it run well. Obviously, you're interested in GPUs since you're attending this course, but we have to recognize that not every machine, not every supercomputer, not every cluster contains GPUs, and we want to make sure that you still get the best experience no matter where you go. So on the subject,
sorry for interruption. Just
sure.
One comment. If you can slow down a little bit, that would be great.
Okay, thank you. On the subject of performance portability, I'm going to highlight an application here called Cloverleaf. Cloverleaf is a mini app that was developed by the Atomic Weapons Establishment in the United Kingdom. And one thing about Cloverleaf is they have rewritten this code for every programming model known to man. They have probably a few dozen different versions of this code available, and they really like to evaluate different programming models using it. So we knew that they had an existing OpenMP version of the code to run across CPU threads, and we knew that they had an OpenACC version to run on our GPUs. And so we asked them to take the PGI compiler, rebuild the code using the multi-core OpenACC target, and see how it compares. And what you see here on the right is the dark blue bar or a gray bar is representative of the performance they got using their hand-tuned OpenMP code. Using their OpenACC code, you see they got comparable performance, and then rebuilding, just changing one compiler flag, you see they got an enormous performance benefit using the GPUs. And there's absolutely no code difference between the blue and the green bars there. And that's something that really excited them a lot, because now they can maintain one code, they don't need to maintain two, and it will work well on a variety of architectures. Now, we wanted to repeat this experiment in-house. Now, one thing I need to point out here, this 30x performance improvement bar is going to change. Here they have, this is a Tesla K80 board, which has 2 GPUs on the board, and they're using both of them. And the comparison on the next 2 slides actually only uses one of the GPUs on the board. So here we took the same code in-house, used a more recent version of the compiler, and what you see is we're comparing against the Intel compiler for OpenMP because that was the compiler that gave the best performance on this particular machine. We then took the OpenACC version on the same machine and built with the PGI compiler, and you can see we have a comparable and then slightly better performance of running across the CPU cores, and then taking the exact same source code with no changes, we're able to run on a K80 card here and get a large performance speed up. Furthermore, without any code changes, only changing the compiler flag to retarget it, we can run on the modern P100, which is our latest high-end GPU, and get an even larger performance improvement. So we can migrate here across 3 distinct platforms, all using the exact same source code and all getting good performance. So just change a compiler flag, and that's what's really exciting about using OpenACC. So let's talk about the 3 steps that we'll be teaching you this week and next week. The first step is to analyze your code, and I'll discuss some techniques in just a moment for doing that. Next, to parallelize your code using OpenACC and using an OpenACC compiler. And then the last step that we'll discuss next week is to apply specific optimizations to your code, and we'll discuss next week what that means. Now, as an example, we've provided in our labs a code that solves the conjugate gradient method. Now, you don't necessarily need to understand what this does, but basically if you view these blue lines as a gradient, what the algorithm is trying to do is find the minimum along that gradient. We've provided you a source code in C and C++ and also Fortran that you could use, but I'm, again, only going to be showing the C here in the slides. You don't need to understand this algorithm to do the labs. However, if you want to read more, I've provided a link here to where you can read more off of Wikipedia. Okay, so our first step is to analyze the code. So what's involved in that? The biggest part of that is obtaining a performance profile. We really need to understand what parts of the code are taking up the most amount of time. It should be fairly intuitive to see that if I accelerate a routine that takes up half the time, that will give me a much greater impact to my performance than one that takes up only 10% of the time. So we really need to understand where our time is being spent, not just at the function level, but really understanding what are the important loops within the code. Also, what are the important data structures? One of the things we've learned from a lot of these GPU hackathons we've held throughout around the world over the last several years is codes that have more complex data structures tend to have a more difficult time getting on GPUs. That's both true with OpenACC and with CUDA. And so understanding the data structure and how your data is laid out will really help with your success. Another tool is to understand the compiler feedback. I'm going to show you some samples of that. A lot of people, they'll build the code, but they won't necessarily dig into what the compiler is doing with their code. And many people don't even realize the compiler will give them this information. But what's critical is to read the compiler feedback and say, okay, here's an important loop, and here's what the compiler did for my code. Or, just as importantly, here's what the compiler didn't do. Why didn't it optimize this loop? And then you can go back and fix whatever is preventing that optimization. Or in the case of OpenACC, what is preventing that loop from being parallelized? And lastly, and this is something that people may overlook, but it's really important to make sure that you understand the code. Some of you are working on very large code bases that have been developed over many decades, and probably don't know every aspect of every function inside your code. And so once you've identified where the important parts are, you really need to kind of understand what that's doing and why the code has been written in this way. Part of understanding the code as well is recognizing, okay, I happen to be doing a lot of linear algebra, so rather than writing my own matrix multiplication, maybe I should be calling into the BLAS. Or I'm doing a lot of FFTs, and again, instead of writing my own FFT, I should be calling into the CUDA FFT library. So that's all part of understanding the code. So the first step we're going to look at here is obtaining an application profile. This really helps us to understand where the time is being spent. Now, if you've done any form of parallel programming before, you may have encountered something called Amdahl's law. Amdahl's law is basically a way of figuring out if I speed up a certain percentage of my code by parallelizing it, what is the maximum performance benefit that I can gain from that? And again, intuitively, you would expect if I parallelize large time-consuming parts of my code, that will have a larger impact overall. So identifying where there are hotspots is really important, and focusing on those hotspots will give us the greatest impact. Now, there's lots of profiling tools available. Many of you have probably used gprof before. gprof ships with GCC, and so it's widely available. Some of you, if you've done some CUDA program, may have used NVProf or NVIDIA Visual Profiler. If you happen to run on a Cray, you may have used CrayPat, or Tau and Vampire or other tools that are available. For this course, because we're really focusing on standardizing on one thing, we're going to be using pgprof. This is available to you in the NVIDIA OpenACC toolkit, or if you just have access to a PGI compiler, it's available with that. And so we'll be using that through this course. I did see the question come in, what was the name of the law? And it's Amdahl, A-M-D-A-H-L, Amdahl's law. Okay, so I'm going to go through a series of screenshots here fairly quickly, but just to give you an idea of the process of using pgprof. pgprof, if you've used Visual Profiler, will look very familiar to you. You'll do File, New Session. This is, of course, after you've built your executable. You'll tell the profiler where your executable is, which I've been showing here. In the case of this sample, which is also part of our labs, it is this cg.x. So you'll see that again as you do our labs. Of course, click Next. And the thing that you want to make sure is checked here is to profile execution on the CPU. Now, I've also checked Enable OpenACC profiling because as we add OpenACC to the code, we'd like to understand the effect it has on the code. So those are the two boxes that I want to make sure you have checked. And after you click Finish, it will run for a while, and finally I'm choosing here under the view to show CPU details because we've not actually started running on the GPU yet. And we'll get this table down the bottom, and I apologize if it appears small on your screen, but this is how it would come up for you. And this table shows us the three most important routines in our code. MATVEC, which we'll look at in a moment, is a sparse matrix vector multiplication. WAXP, which is again a linear algebra, and DOT, which is another common linear algebra operation. This fourth one here, allocate 3D Poisson matrix, I happen to know from looking at the code that that's just an initialization routine, so it's one we can safely ignore. Now, what's really useful is once I have that, if I were to double click on one of these, so in this case I'm going to double click on MATVEC because it's the most critical one, pgprof will pull up the source code for me. Now, what I didn't show here is that it will pop up a dialog to ask you where to find your source code, but it only does that once, and then it'll know from there on. So here is the most time-consuming routine, and we can look at this and recognize from these doubly nested loops and the general operations here that this is doing a matrix vector product, and it is in fact, we would dig down a little bit further and find out that it's doing this across a compressed sparse row matrix. But that's some of the details that you can dig in as you analyze the code yourself. Now, looking at this code, again, I can see what it does, but it's really useful to understand what the compiler understands about the code. And so for that, we're going to turn on compiler feedback. So before we make changes to the code, let's understand how the compiler is optimizing the code. And with PGI, this is done with the minfo flag. Incidentally, there's also an mneginfo flag that I've used in the past because sometimes knowing what the compiler didn't do is actually what you want to find out. So minfo and mneginfo, and that's this is the line down the bottom here is how you would apply that to your code. Minfo equals all. That all says tell me everything you know. And this CCFS is a way of getting this information into the tools, so which you'll see in a moment how that works. On the right, you can see the feedback for that MATVEC function, and it tells us, okay, it was located in matrix functions.h at line 23. and it tells us some of the optimizations it performed on the loop. But what's really even more useful is if we look at that back in pgprof, because now inside the source code, if I hover where this little black arrow is, it tells me this line of code, this loop at line 18, it's generated vector instructions for it, and it's also generated some prefetching, and so it tells me what the compiler did. And as I said, sometimes it'll tell me what the compiler couldn't do. Now, this notion here of intensity, let me explain that one for a minute. So intensity, or computational intensity, is a measure of how much work you're doing in relation to how much you are communicating with memory. So if we think about just any operation we do, let's say we want to add two numbers together, numbers A and B. Well, I need to fetch A out of memory, so that's one load instruction, which is a memory operation, and B, it's a second load instruction. But I only have one actual math instruction there, which is the addition. So A plus B actually has a computational intensity of 1/2. There's one math operation and two memory operations. So what this measure here is telling me is that there's an equal measure of memory operations to arithmetic operations. So that tends to be significant in understanding what will be beneficial to move to the GPU. See, things with a very high computational intensity, well, that means that when I load something out of memory or when I move a piece of data to the GPU, I'm going to compute on it a lot. And that's really useful in ensuring that what you move to the GPU, that you'll make good use out of it. So high computational intensity, 1 or greater, is a really good hint that this will run really well on the GPU. Low computational intensity doesn't mean that it will, but it does mean that you're probably going to need to move other things to the GPU to kind of offset the cost of going there. Okay, so we've done our analysis. We understand where our time is being spent. Now let's begin to parallelize our code. So the parallelize step involves inserting OpenACC directives to our code, and OpenACC directives are applied to the most important loops. So we've identified this loop nest inside of MATVEC as one of the important loops inside our code. We also need to enable OpenACC in the compiler to make sure it's going to build, and build in this case for a GPU, and then finally run on a parallel platform, and of course I'm going to be doing that on an NVIDIA GPU. The cartoon to the right kind of gives you a big picture of what's happening. These rectangles down the middle, well, that's supposed to represent the flow of your application, and OpenACC applications always begin on the host CPU. And we begin running on the host CPU, and eventually we'll encounter some time and compute-intensive part of the code, and that's what we're going to move over to the GPU. Ideally, if your code has some small number of routines that take up a significant portion of the runtime, that's kind of an ideal situation. You can move those over, run them on the GPU, and then move them back. Some applications are not so lucky. They may have 20 functions that all take up about the same amount of time, and those tend to be a little harder to move. The rest of your code runs on the CPU, and execution always begins on the CPU and ends on the CPU. And hopefully more and more of your code will get offloaded in the middle here. So accelerated computing really is around using both the CPU and the GPU that you have. On the left, we have kind of a cartoon of a traditional CPU here where we have 6 blue boxes to represent probably 6 CPU cores. And CPUs are really optimized for serial tasks, so do a sequence of operations in order and doing that very quickly. Whereas GPUs are actually optimized for parallel tasks, and you can really see that in the hardware. CPUs have a small number of very fast cores. GPUs have a large number of relatively slower cores. But let's go into a little more detail about the trade-offs. So CPUs do have their strengths. CPUs tend to have a very large main memory, at least compared to the GPU. On a laptop, you may see 8 or 16 gigabytes of main memory. On a workstation, you may see as much as a terabyte of main memory available to you on the CPU. CPUs also have very fast clock speeds. This is what enables them to run sequential operations very quickly. Now that comes with a trade-off. Very fast clock speeds mean that these cores are very hungry, and we can't allow the cores to get stalled out for any reason. So things like memory latency can be very costly on a CPU, and CPUs have optimized away memory latency. So let's talk about memory latency. Again, going back to my adding two numbers together, A and B, in order to do that addition, I need to request the value of A from memory. So from the time that I make the request to the memory subsystem saying, give me the value of A, to until that becomes useful for me, and it's available for me to use, that is the memory latency, from the time of the request until the request is filled. Now, for a CPU, the way CPUs operate is we put things in cache. So we eat the cost of going to memory once, but then we try to keep data as much as possible within the cache so that the cost of going to memory is reduced. By doing that, we can keep the CPU ready to go, and the CPU cores are ready with the data that they need. This does mean if you have a small number of threads, so typically on a CPU you would have one thread of execution per CPU core, though it can run very quickly. But the CPU has some weaknesses. The cost of having very large memory is the bandwidth of that memory is relatively lower compared to the GPU. You're looking at DDR3, DDR4 memory usually on a CPU. Also, cache misses are very costly. So we really need to keep the latency down as much as possible by having as much as we can in cache. But if we miss cache or something else happens, like a branch misprediction or something like that that causes the CPU core to stall out, that can be really costly, on the order of hundreds, thousands of clock cycles that the CPU is just not able to utilize. So it's very costly. And the CPU will do a lot to try to keep that from happening. But at the end of the day, because the CPU has to put so much space towards caches and put so much logic in branch prediction, in cache prefetching, and out-of-order processing in order to keep these cores busy, more of the power goes to that and less of the power goes to computation. And so that means it has a relatively low performance per watt. Looking at GPUs, GPUs have extremely high bandwidth main memory. If you're looking at a Tesla P100, which is our current top-of-the-line board, you're looking at over 700 gigabytes per second of main memory bandwidth. We also have significantly more compute resources. So all of that space that the CPU had reserved for caches and things like that, we're able to dedicate to compute resources. So we are able to do a lot more with our space. Now, the way we do that is kind of neat. So instead of worrying about trying to reduce memory latency as much as possible, we have built an architecture that is latency tolerant. And the way it's latency tolerant is we use a lot of parallelism. So if I have requested the value of A from memory, the hardware knows that I, as a thread, can't continue executing until A gets back. So it goes and it finds a different thread that is ready to execute, and it begins executing that. And so as long as we have enough parallelism to ensure that there's always something ready to run, then that we can completely tolerate the latency to memory. And from my perspective as a thread, what I know is I was running, I requested A, and the next time it was my turn to run on the hardware, A was there, and as if there was no latency at all. So we really require a lot of parallelism, and by building a latency-tolerant architecture, we're able to dedicate a lot of space to that parallelism. This results in a very high throughput of calculation, and I'll discuss that term throughput on the next slide, and a very high performance per watt. Now, GPUs do use more raw power than CPUs, but we are able to do a lot more with that. Now, GPUs do have their weaknesses, relatively low memory capacity. So again, looking at a modern P100, you're looking at 12 to 16 gigabytes of memory per GPU. Even on a Tesla K80, which was our previous top-end card, you were looking at 12 gigabytes of memory per GPU, and it just happened to be 2 on the board. So the memory capacity is generally lower than the CPU, and the per thread performance is lower. So if you're only running one thread of execution, a CPU is going to do it a lot faster. GPUs will do it much more slowly. But by having lots and lots of threads, the net result is high throughput. So let's talk about speed and throughput. Now, if I want to get home, and I want to get home quickly, I might look at hopping on a motorcycle. And motorcycles can get places very fast. They can do a lot of tricks as long as I'm willing to do them and to try to get through traffic as quickly as possible. And unfortunately, some people do some really extreme tricks to get there quickly on a motorcycle. So if my net goal is how fast can I get home, a motorcycle is an outstanding choice for me. But let's say I need to take lots of people with me. A motorcycle is not a very good choice for that. I can take at most one passenger along with me, so I have some choices. I might have to drive home, drop the person off, come back and get the next person, and keep going back and forth. That's not a very efficient operation. Another option would be to buy a lot of motorcycles and everybody go pair up and go, but that's first very costly to have a lot of these motorcycles, but it also begins to clog the road up, and we can't get there quite as fast because there's so many more motorcycles on the road. So so for transporting a lot of people, a motorcycle is not a very good choice. In fact, a bus would probably be a better choice. So here I'm showing a double-decker bus, and I'm going to estimate the capacity at 100 people. So if I want to move 100 people, that bus is not going to go as fast as the GPU, but in the time that it takes to get there, it's going to move a lot more people. So let's say I have 100 people on that bus versus the 2 people on the motorcycle. Well, even if I get there and it takes twice as long to get there, I'm still 25x more efficient at moving people. So it really depends on what your goal is. If your goal is to get one thing done fast, then the motorcycle is better. But if your goal is how efficiently can you move a lot of people, then the bus is better. And the same is true with your science. Most scientists I know and most HPC programmers I know have a bus load of data that they need to work through, and for that, the GPU is going to be able to handle it better through high throughput. So here's what our nodes are going to look like. We have a CPU on the left with its main memory, and a GPU on the right with its relatively smaller main memory. And for most machines out there, unless you happen to be fortunate enough to have one of the brand new IBM machines with Power 8 and Pascal P100 GPUs, most machines are connected between the CPU and the GPU using PCI Express. And any time that I want to run on the GPU, I need to copy the data from the CPU to the GPU, and this has to be done over PCI Express. So PCI Express is relatively low bandwidth compared to memory. So obtaining high performance on the GPU nodes often requires reducing this PCI Express copies. Now, we're going to kind of ignore this problem for this week and revisit it next week. And what's going to enable us to ignore the problem is using something we call CUDA unified memory. So we can either look at the CPU and the GPU as having 2 distinct memories and have to manage the data in each, or starting with CUDA 6, so it's been around quite some time now, we have CUDA unified memory. So a unified memory address is something that both the CPU and the GPU can view. And the underlying data that's represented by that address will be moved between the CPU and the GPU as necessary. Now, unless you happen to have one of the new Pascal GPUs, the older GPUs, the Kepler generation, the Maxwell generation did this in software. The new Pascal GPUs are able to handle this in hardware, making that much faster. Now I'll note that this is sometimes known as managed memory, and you may hear me referring to it as such sometimes. So we're going to use this feature to get up and running this week, and then next week we'll revisit this and look at explicitly managing our data. So let's start putting our computation on the device. First, we're going to use the OpenACC parallel directive. The parallel directive, like the name implies, simply generates parallelism. It's very fairly simple to understand. So here I have an ACC parallel pragma, and I have some curly braces here to denote where that parallel region begins and ends. And this blue arrow here is my execution through that region. So when I encounter a parallel directive, the compiler is going to generate parallelism for me. And what we call this in OpenACC is we're going to generate one or more parallel gangs. I know gangs would not have been my first choice for names, but that's what we call them. These are gangs. And something to note here is I've generated the parallelism, so I have these 6 gangs to run in. But at the moment, this blue thread that was running once here on the host is now running 6 times on the GPU. So I have the resources to run in parallel, but I've not actually distributed my work at all. In order to do that, I'm going to use the loop directive. And so here again, I have my parallel directive here to spawn the parallelism. The loop directive identifies which loops I want to run in parallel. So I have a for loop inside of my parallel region, and immediately before that, I put a pragma ACC loop. So it's informed the compiler, this is the loop that I want you to parallelize. And what it will do is distribute the n iterations of that loop to my parallel gangs. Now, there's something really powerful in this. This ACC loop directive here, when I've used it inside of my parallel region, has told the compiler, here's a loop that I believe you should parallelize. And it's also made a promise to the compiler that all of the iterations of this loop are independent of each other. And what's powerful about that is by informing the compiler, hey, here's an independent loop, I'm also informing the compiler, I don't really care how you run the loop. I don't care if you run it forwards or backwards. I don't care if you run 1 iteration per gang or 100 iterations per gang or run all of them within one thread. It really doesn't matter in order to get correct results. And so now the compiler can take that and understand, okay, if I'm building for a GPU, I want to build and distribute those n iterations widely across the GPU. Or if I'm building on a CPU, I may want to do something different. So that's a really powerful thing. Now note that parallel and loop are so often used together that we do actually have a shorthand for it, and it's simply ACC parallel loop. And so that just combines the whole operation into one. It generates the parallelism in the form of these 6 parallel gangs, and it identifies the loops to go together here. So all of that happens in one step. Now, I am going to go forward and begin applying to this code, but let me take a second here to see if there's any questions that really that I should address soon. We'll talk about that one a little bit later. So there is someone pointed out here that they had experience with OpenMP and OpenMPI, and sometimes OpenMP did not give acceleration and OpenMPI did not. So OpenMP and OpenMPI are 2 really distinctly different things. OpenMP is a threading model, and OpenMPI is actually an implementation of message passing. And so probably what was happening in that person's case is the MPI was forcing you to think about the way your data is laid out in order to get better performance. OpenACC as a programming model is more similar to OpenMP. It is actually very, very closely modeled after OpenMP. And so you may face a very similar situation where you'll need to take and understand your data, understand how your data is accessed in order to get the good performance with OpenACC. Some of these others, I think I'll specifically answer in the later part of the session here. Does OpenACC take advantage of SIMD operations? And it can on SIMD architectures. So in the optimization topic next week, one of the topics will be informing OpenACC to use vector operations, which is what a SIMD is. Okay, most of these look like good questions to answer later, not directly applicable to this part of the lecture. So I'll go ahead and move forward. So now that I've introduced to you the parallel loop directives, now that I've introduced those, let's talk about how to apply them to the code. So as part of this case study, we'd like to parallelize that conjugate gradient code I showed you. And most of the time when you're doing this in a real application, you want to start at the most time-consuming function and work your way down. As I said, that will give you the most bang for your buck. However, in this specific example code, I'm going to do it completely upside down. And the reason for doing that is I want to introduce the concepts to you in a simplified way. So I'm going to start with the easiest to accelerate function and then work my way up to the hardest. So in a real application, I probably would not do it in this order, but I do want to teach these to you. So we're actually going to start with WAXB. Here on the left, I'll show you the WAXB code. I've stripped out just a little bit of variable declarations, but it's a pretty simple loop. Each iteration of the loop calculates one value into this W coefficients array, and it uses the X coefficients array and the Y coefficients array to do this. So one of the things I can observe here is every loop iteration calculates into exactly one space. So there's absolutely no data dependencies within this loop. There's no chance for iteration 1 to affect any other iteration in the loop. So this is a completely independent loop and something that's very straightforward to parallelize. So all I've done here is add my Pragma ACC parallel loop over top of my existing loop here. And so what I've told the compiler here in one line is, first, generate parallel gangs. That's what the parallel stands for. And next, take this loop, this for loop, and distribute that across those parallel gangs. And that's pretty straightforward. That's really, in the most simple cases, that's what's required. So now that we've added that into our code, we need to inform the compiler to build OpenACC, and so that's done with PGI with the TA flag, which stands for Target Accelerator. And so I've added the following compiler flag at the bottom to the make file: TA Target Accelerator equals Tesla, so NVIDIA Tesla GPU. I've used the managed sub option here. That's so that we can get this CUDA unified memory that I talked about. Next week, one of our goals is to take that out. And this last part, line info, is actually just something to give some additional information to the tools. It's really not needed, but when you have it, sometimes PGProf will give you some additional information. So that's why I've put that there. And because I have my compiler feedback enabled to the compiler, you can see on the right is what is printed out. And it tells me it encountered the WAXB routine. It's located at line 22 of vectorfunctions.h. And the important parts here, we'll ignore these other messages for now, are that it did find code that it could generate an accelerator kernel. So a kernel is just the parallel execution of that loop, and it generated for an NVIDIA Tesla. So that's the important part that we really want to see that tells us that we were successful in parallelizing our code. Now, if we run it at this point, it turns out we're going to get absolutely terrible performance. And again, that's because I'm purposely working backwards here. The PGProf would show us something like this, where these tiny little greenish, bluish slivers down the bottom are our parallel loop. And all of this brown we see up top is data moving back and forth between the CPU and the GPU. Now, if you think about what we're doing, it makes sense that this would happen. We have accelerated one of our 3 routines. The other 2 are still sitting on the CPU. So if I execute WAXB, I'll copy my data, I'll execute WAXB, and then the very next time that data is needed, it has to come back to the CPU. And so that's really expensive. If we actually zoom in, we can really emphasize the fact that a tiny little sliver of time is being spent computing and the rest of the time is spent moving data. This is to be expected because we haven't moved enough of our code over to the GPU yet. So in order to prove this, what we're going to do is we're going to move our other 2 functions to the GPU. This is why inside your real codes, as you begin accelerating, you really want to find the most key routines, accelerate that, then kind of find what is the next thing that gets used and accelerate that, because we want to enable the data to stay on the GPU as long as possible. And that's exactly what we're going to do here, is we're going to go and accelerate the other two important functions. Dot is a fairly straightforward one again, but it does have one additional complication. So all n iterations read from x coefficients and y coefficients. But what's different about this function is they're not storing into an array, but every single value here for every single loop iteration gets multiplied together and then added into sum. So we're calculating, we're multiplying x coefficients times y coefficients. We're multiplying that n times, one for every loop iteration. So we'll have n copies of that, and we need to reduce that down to 1. And the way we do that is by adding them together. So this is what's called a parallel reduction. We're reducing from n values down to 1. And in order to do that safely in parallel, we need to tell the compiler, hey, there's a reduction inside this loop. So I've identified, using this additional clause here, reduction. The operation that we're using to reduce is plus. That's, in my experience, the most common one, but there are max and min and multiplication and things like that. And what variable are we reducing? We're reducing sum. So that's why this one is just a little slightly more difficult. Now, something to note here, if you've never done parallel programming before, is that when you do a parallel reduction, so in this case we're adding floating point numbers together, because floating point numbers are not precise, it does mean that your answer may change slightly. And I'm not talking about huge amounts, but I'm talking about a few of the small, least significant digits could change. And this is not because the answer is wrong, but this is because the operations are being done in a slightly different order. So you may find yourself, your answer is kind of shifted just a little bit from what you're expecting. And keep in mind that that's because we're now operating in parallel, so the order of operations is a little bit different. So the answer is not wrong. It's just due to the nature of floating point math. And if your code is really sensitive to small numerical differences, then you'll need to do something to address that in your code to make sure that you're able to handle the fact that you're not going to get the same answer as adding them up sequentially. Now the final routine we need to accelerate is matvec. Again, this one is slightly more complicated. We'll kind of build on the past knowledge. This is actually a doubly nested loop. So I'll put my ACC parallel loop on the outside. And then on the innermost loop, I'm going to once again do an ACC loop and expose the reduction that it's doing. So the parallel loop generates parallelism and parallelizes I. And that innermost loop directive tells the compiler all the iterations of J are independent, but it does need to do a parallel reduction. And that's really all we need to do on this function. So it's only slightly more work. It's really important, though, when you have nested loops, if each loop in the nesting tree is independent, it's really useful to tell the compiler that, because otherwise the compiler has to do its own analysis to decide that, and sometimes compilers get that wrong. So the more information you give the compiler, the better chance of success. And if we rebuild this and rerun this, and I don't need to make any further changes to the makefile to make that happen, pgprof will look something like this. And what you see down below first is these green bars down here and these tiny little slivers are the computation happening on the GPU. Up top, notice all my brown bars are gone because my data doesn't need to migrate back and forth anymore. All of my calculation is done on the GPU, so my data just stays on the GPU. One further thing, if I zoom in, you'll notice that pgprof and NVIDIA Visual Profiler are OpenACC aware. So at the top you can see a bar that says, hey, this part of the code, you should go look at vectorfunctions.h. And it gives you some information, and the more you zoom in, the more information you'll see there. So that's really useful to help in debugging your code. pgprof does that, and a few other tools such as Vampire and Tau do that as well. Now, I do need to note that this important function down here, which if you kind of sort of stare at the name, you'll recognize that this is matvec, which is our big kernel. we're going to optimize that next week. There's some optimizations we can do. The compiler is able to parallelize it, but there's some things we can do to make it better, and so we'll do that next week. But I'll go ahead and show you what the performance looks like now. So I have my original serial code. Because, again, OpenACC is not a GPU programming model. It's a parallel programming model. I can actually run it in multi-core on the CPU across CPU cores, and you can see I get actually a fairly nice speed up. So I get about a 6x, 6.5x speed up across 16 cores. On one half of a K80 board, I see a slight speed up. It's not as substantial as I would like, and that's because we're going to optimize it next week. But you do see a little bit of a speed up. And lastly, if I run on a P100, we see even greater speed up. Now, I want to kind of tease you what's going to happen next week. Next week, we're going to optimize, and if I can get this to advance, you'll see we'll actually get much greater performance. We'll more than double the performance of the CPU versions of the code. And again, since we're only running on one half of a K80, that's why this one is actually slightly less than the CPU socket. The significant thing to remember here is we've taken our code and we've parallelized it, and we can run it across a variety of architectures. That's really, really important for you. And the reason I choose a code here where I have to optimize later is I want to give you a more realistic expectations. I could easily choose a code where the compiler just works and gives it enormous speed up one time, but then when you go back to your application and it doesn't just work and you don't get 100x speed up with one line of code, that you don't get frustrated. I do want to show you that some codes do take some additional optimization. So come back next week and we'll talk about what those optimizations are. So that's the next step. And I'll show you that we'll get some new performance profiles. We'll look at the data and say, okay, well, we're getting this speed, but what is keeping it from getting faster? We're also going to remove unnecessary data transfers. So currently, we're relying on CUDA managed memory, which is unique to NVIDIA GPUs. Let's take that out and make sure that the result is a code that can be run anywhere. We're going to look at how the compiler takes the loop iterations and maps that to the GPU hardware and distributes it to the hardware and see if we can do better. And, spoiler alert, we can do better, and we'll get about a 2x performance improvement. And then I'll also discuss some common pitfalls that you may need to refactor around. So, keep in mind, keep tuned for that. So before we switch over to the Q&A session, I do want to introduce you to our Quick Labs service. So NVIDIA has some online training available to you, and as part of this course, you're going to be given credits so you can take these online labs. So I'll leave this up here for a moment, but the link will be posted later on. If you go to this site off of developer.nvidia.com and sign up for a Quick Labs account and use the promo code OpenACC, you'll receive a certain number of credits, and it should be enough credits for you to do all of our OpenACC labs. If you've done this before, this coupon code won't work for you because it already has your email in the system, but please just email us, openacc@nvidia.com. Let us know that the code didn't work and that because you've used it before, and we'll add some additional credits to your account. So don't feel like you've missed out. We'll definitely make good on that. And go ahead this week and get signed up. If you'd like to, there are some labs there, and I would encourage you to take a look at the lab that's titled 2x in 4 steps. Now, notice, of course, that we were promoting 4 steps then, and we're only promoting 3 steps now. So the process is a little bit different than what I've been teaching. But if you just can't wait to get started, that's the one I would recommend starting with. And then the other labs that are based on this same conjugate gradient example, we'll look at those after next week, so when you've seen the entire picture. Some more things I want to promote before we go to Q&A. If you're looking for an OpenACC compiler, I did see a question earlier, is there a free OpenACC compiler? If you are affiliated with any university, you can get the OpenACC toolkit for free. This includes the PGI compiler, the PGProf profiler, several CUDA libraries. All of that's available here at OpenACC toolkit off of the NVIDIA developer site. If you're not affiliated with the university, you will still get a free 90-day trial. So that's 3 months that you can look at what this will do for your code. Also, I'll note, since there was a question about the free compilers, the GCC compiler does now, the latest version does support OpenACC, but it's not complete support yet. So it's certainly not as mature yet as the PGI compiler, but it is available for you to begin experimenting with. But if you can get the PGI compiler through the OpenACC toolkit, I would encourage you to do that. If you're looking for additional help, there is a new book coming out in just a couple of weeks. This was written by a variety of authors. There's probably 12 or 15 authors. I've contributed 2 chapters to it, and that will be available in the coming weeks. And lastly, I'll point out that since you're taking this class, some of you are taking it because it's part of your college course, and some of you are taking it because it's something you're interested in outside of that. So if you'll attend the lectures this week, next week, and the following week, we're putting together a certification exam then just to kind of demonstrate that you paid attention and that you did actually complete these lectures and the labs. You'll be entered into a drawing for a Titan X GPU or one of several copies of the OpenACC book that's coming out. And we'll also send you a certificate so that you can demonstrate, if you are a student, you can demonstrate that you did complete the course. So lastly, if you do find yourself in need of help, you'll find the recordings at the link here, which I listed earlier. You'll find some help at the PGI website, which is pgroup.com, or I would really absolutely encourage you to post any questions on Stack Overflow and tag them with OpenACC. That will come to more than just me, but come to a lot of us who monitor that forum there. So please post your questions there, and that way, once you get your answer, that knowledge is out there for other people if they hit that problem as well. And then finally, you're welcome to email openacc@nvidia.com if you run into any issues. So I'm going to switch over here and start going through some of the Q&A questions. One question is, are there any automated optimization features and how reliable are they? And there absolutely are a lot of automated features. So if you look at the PGI compiler or other mature OpenACC compilers, such as the Cray compiler, possibly even the Pascal compiler, these compilers kind of have a history of doing things like automatic vectorization, automatic parallelization, even in terms of reordering loops and blocking loops. And so the compiler is free to do that. And one of the things that makes it possible for the compiler to do that is the fact that as part of putting in my OpenACC, I have told the compiler, hey, these loop iterations, they're independent of each other. So I don't really care what order you've done them. And so that really gives the compiler a lot of freedom to know, okay, well, if I reorder these loop iterations, if I block them, if I change the order of these 2 loops and interchange them, I'm still going to get legal and correct results. And so many of the compilers will do further optimizations. How reliable are they? Well, I'm not sure exactly what to consider reliable. I have had very positive experience with the OpenACC compilers I've used. Sometimes I'll encounter a case where the compiler took a wrong guess, and as we'll discuss next week, there are ways to inform the compiler, here's the specific optimization I think you should take. All right. Next up, let's see. There are any free compilers? I answered that one. To use OpenACC, what do we need to install on our machine? The best case that I would suggest is to download this OpenACC toolkit. The link is up there currently, and that will give you everything you need to get started. It will provide you a compiler, libraries, profiler, even some instruction books that are available to you. So that's the best start. If you also could choose, if you'd like, to download a recent version of GCC, but typically with the GCC you would have to build the OpenACC support yourself, so it's a little bit more difficult to use. So comparing the advantages and disadvantages of OpenACC versus Numba and how involved is NVIDIA with Numba development. Now, I'm not certain of the answer to how involved NVIDIA is with Numba, but I can talk about some of the similarities and differences. So Numba is a Python library or implementation that can be used to run on the GPUs, and I've actually seen it used in a few places. There's some tutorials we've put up on the NVIDIA developer blog showing how to use it. Now, if you're already writing your code in Python, Numba is a great way to do it. It has a lot of similarities with OpenACC, where you can inform the compiler using function decorators, hey, this is a function that I want to run in parallel, and it will decompose that for the GPU, generate a GPU kernel for you, and handle all of the data movement. So it's very similar in that respect. One difference, a major difference, is that Numba is a Python-based approach. OpenACC is available for C, C++, and Fortran. So there's not currently any support for OpenACC if you're a Python developer, other than perhaps calling into it under the hood. How much is the performance different with OpenACC compared to programs running in CUDA? And that's a little bit of a loaded question, but I'll answer it as best I can. It's difficult to make the comparison, because in order to do that, we would have to have both versions of the code, right? An OpenACC version and a CUDA version. In the few cases where that does exist, what we're finding is it's typically possible to get in the range of 80 to 90% of OpenACC code. I just encountered a code last week. They spent several days writing CUDA kernels, and then just for experimental purposes, rewrote an OpenACC version, and it took them actually just a couple hours to do it in OpenACC. And the OpenACC version was a little over 80% of the performance of their hand-tuned CUDA. So what would cause CUDA to perform better? If in CUDA you're doing a lot of low-level optimizations that involve things like using the shared memory on the GPU device, using other types of memory, the texture memory, constant memory, any of these sort of special memories, or if you're specifically counting on doing a particular type of coordination of threads within a thread block, those sorts of low-level optimizations are very difficult to represent in a high-level language like OpenACC. And so codes that are able to take advantage of those will outperform OpenACC. Codes that are not able to take advantage of that, or you'll expect the performance to actually be quite close. And I have even seen a few rare occasions where the OpenACC compiler beat the programmer's CUDA code by doing things slightly differently. So the performance, the compilers really aim to be somewhere upwards of 80% if possible. Of course, it will vary from code to code. Is it possible to use OpenACC with Fortran? Absolutely. C, C++, and Fortran. And actually, Fortran developers are particularly fond of OpenACC. Fortran makes a lot of promises in the language that tend to make it a little bit easier for the compiler to parallelize than C and C++. So Fortran is absolutely usable with OpenACC. Why did we make OpenACC when OpenCL does the same thing? And actually, OpenACC and OpenCL are very different. OpenCL is a very low-level language, so I would write a function in the form of an application kernel, and I would use a lot of kind of boilerplate in order to launch that either in parallel on a CPU or in parallel on a GPU or another device. It's a very low-level language, and you're writing, as a result, while the boilerplate part of the code is very portable, you frequently have to write different application kernels for different architecture, except for in the most simplified cases. OpenACC is designed to allow you to stay in your language of choice, so C, C++, or Fortran, and let the compiler do the parallelization for you. So it is guidelines and hints to the compiler to have it generate the parallel code, whereas OpenCL, it's very, very low level, and you have to learn a completely different programming paradigm. So they're actually quite different. Would OpenACC replace CUDA someday, or are these two models useful for differing reasons? And in my opinion, they actually do both bring different things to the table. OpenACC is a great on-ramp to get started. It's a great way to rapidly accelerate your code. but as I noted earlier, you don't always get the low-level optimizations that are available. OpenACC is also portable to a variety of architectures, so you can take it to a multi-core x86 CPU, you can take it to a multi-core ARM CPU, you can take it to an AMD GPU if you'd like, and all of these are available to you. CUDA is something that NVIDIA develops that is very closely tied to our hardware. We really develop CUDA along with our hardware, and it exposes a lot of low-level hardware features. So they really do have differing goals. If your goal is, I want to run as fast as humanly possible on an NVIDIA GPU, CUDA is probably your best solution because you really can get into the performance details and really map it to architecture. OpenACC is a higher level approach that allows you to kind of stay in the language you're used to, stay in the language that you're comfortable with, and not make large significant changes to code. Now, one thing I like to promote, and I didn't include in this particular talk, is that OpenACC is one part of the strategy. So we actually view GPU programming can be done in 3 different ways. One is to use accelerated libraries. So if you happen to be doing a lot of common math operations, you can do accelerated libraries. Compiler directives like OpenACC allow you to rapidly put things on the GPU, work very quickly through the code, and incrementally add that to the code. And then when you reach a point that you have everything running on the code with OpenACC, and you have one particular function that absolutely needs to be as fast as possible, you can rewrite just that limited part in CUDA and get the best of all worlds. And OpenACC is interoperable with CUDA, and so you can do it that way. And I'll have some examples of that in a later lecture. Is it possible or planned to run OpenACC somehow with Python? Not at this time, and it's actually something that I was talking with someone about just yesterday. So Python, as I mentioned earlier, does have Numba as one option for running Python on the GPU. Python does not have a notion of decorators on loops, and so it's really kind of a different sort of approach. We would have to kind of fight through that, and so at this time there's really no plan for that. It would be interesting to I would be very interested in seeing someone prototype it though, because I think there's definitely some interest there. I see things.
Let me interrupt for a second.
Yeah.
I just want to remind everyone, if you can, please submit your questions for the Q&A pod. That will be way easier for us to monitor that we answered those or not. In the chat, we might lose your question. And if we haven't answered that, there are a lot of questions, so we will be answering them after the call as well. Okay, thanks, Jeff.
Sure, and actually I was about to say the exact same thing. I was seeing things coming by in chat, but I'm only really reading the Q&A right now. Does ACC take advantage of SIMD operations? And with at least the PGI compiler, it does. And so you'll see it generate SSE and AVX instructions on x86 and the equivalent instructions on other architectures. How much extra overhead would OpenACC directives add to the existing CPU-optimized algorithm running on a CPU? And that's an interesting question. So OpenACC, when implemented on multi-core, at least in the PGI implementation, a parallel region or a kernels region, which I didn't really discuss here in this lecture, which is another directive for generating parallelism, would generate CPU threads. And so the same overhead would apply as using pthreads or as an OpenMP. There is some cost to generating those threads, but the implementation will reuse those threads as much as possible. So really once we have the parallelism generated, what I've found is that actually we're able to, in most cases, an OpenACC code is able to run comparably well as an OpenMP code or a pthread code would. Now, some people do like using MPI instead, and MPI is, if you're not familiar, is the message passing interface. One advantage that MPI has is that it does force you to really concentrate on the locality of your data and how your data is decomposed. And so I have seen cases where MPI programs will run a little bit faster, and it really comes down to the forcing you to think about the memory in that way. So the short answer is very little overhead would be added by OpenACC. Can I pair OpenMPI with OpenACC and send 4 processors and each processor call the GPU? Absolutely. That's been done in several codes. And we'll have an example in the final week where we do exactly this, but you can use OpenMPI or MPI in general to run multiple processes. Each process can either have its own GPU or they can have multiple GPUs. And you can even use a GPU-aware MPI like OpenMPI and pass data directly from the GPU to another GPU with OpenMPI and with MPI and OpenACC. So absolutely, and watch for an example in a few weeks. Or if you'd like, if you can't wait, go check out the course that we previously gave, the Advanced OpenACC course that we gave in the spring. There is a question about, I used Ellis Dalton as an example, is the version mature? And I don't want to speak for the developers. I do see you noted that you know one of the developers. They are using it in production, so they at least are able to run the particular science that they're interested in. But you would have to speak to them about the maturity. I'm not certain what their support plan is. So it says here, in the past, OpenACC was costly. Is it now truly open source? Are there any costs involved, like royalties? OpenACC has always been an open standard. It is free for anybody to implement. The specification has always been online, freely available, and anybody can implement it. Now, the cost involved is if you would like to become a member of the organization to work on the standard, there is a cost involved in that. So organizations like NVIDIA, Cray, several universities, Oak Ridge National Lab, Pascal, a lot of these corporations and universities and organizations have paid into OpenACC to participate in its development. This is typical for all language standards. The same is true for C, C++, Fortran, JavaScript, all of these. The same is true that they are managed by a standards body. And so the people designing the language do pay into it, but the people using the language, there's no royalty to that. It is a fully open standard. So there was a question here, and I think I'm missing some context in here. So if you'd like to ask it again with a little more context about the performance comparison between PGI and Intel on CPU using OpenACC, the PGI compiler is able to run OpenACC across CPU cores on Intel and all x86 architectures. The Intel compiler does not support OpenACC and therefore cannot make that direct comparison. However, if you have an OpenMP code, as I demonstrated earlier, the PGI's OpenACC on the CPU was comparable in performance to the Intel OpenMP implementation. If there's more details you'd like, please post a follow-up question. Is multi-GPU K80 enabled? So with a K80 card, if you're not familiar with that particular board, it does have 2 different GPUs, and although it's one board, they are programmed separately. The same is true if you're doing this in CUDA or OpenACC, or Python for that matter. And so the reason the data that I showed for K80 was on one of those is because you do have to explicitly manage them separately. So I do have an example that comes up in the 3rd week of the course where we break up the work across multiple GPUs, and in that case, because we've blocked the work to go across multiple GPUs, we can run across both parts of the K80. But you do have to do that explicitly, just as you would with any other program model on the K80. I already answered earlier about the differences between OpenCL and OpenACC, so I'll mark down his answer, but post follow-up questions you like. What are the main differences between CUDA and OpenACC? And again, I answered that one a little bit earlier, that CUDA is a very low-level programming model. OpenACC is a very high-level programming model that's designed around advanced compilers. What are the compiler flags to compile OpenACC for GPU or CPU? Let me go back a couple slides here because I show one of them. It is right. Here you see here we have a TA equals Tesla. That is building for a NVIDIA GPU. We use Tesla because that's the high-end GPUs, but it will work on GeForce GPUs as well. If you want to run a multi-core, you would say -TA equals multi-core. And if you have an AMD GPU, you can also do a -TA equals Radeon here. So if you do PG C++ or PG Fortran -help -TA, it will give you a complete list of what all those options are. Can I use OpenACC directives inside of CUDA kernels? That's a great question, and no, not at the moment. But you can actually do the reverse. So you can take an OpenACC code, you can have it call CUDA kernels directly. What you would do is pass your data from the OpenACC into a CUDA kernel, or you can even use CUDA device kernels and call those functions inside of OpenACC loops, and I'll demonstrate that in the third week. Or if you'll search online, I have some examples. Search for OpenACC interoperability on GitHub, and you should find some examples where I've done exactly that. So you cannot call OpenACC inside of CUDA, but you can do the reverse. Do OpenACC and Theano mesh together? In theory, yes, although in practice, I don't know anyone who has tried it. So Theano is a deep learning framework that can be run on GPUs. And just like with CUDA, I can manage my memory using OpenACC and call into any GPU accelerated library and pass that data in. The directive for doing this is called host_data, host data. There's examples in the final week of the course of doing exactly that, or as I said a little bit earlier, if you search on GitHub for OpenACC-interoperability, that's the name of a repository I put up there with a whole bunch of examples, and the same trick should work for Theano, but I've never actually tried it. But in high level, it should. What other languages are planned to be covered with OpenACC? At the moment, we are only directly planning on C, C++, and Fortran. I know there is some interest in Python, but there's also some challenges that the Python language may not be able to support that. And so, right now, C, C++, and Fortran are the languages that we do support and plan to continue to support. Is it possible for OpenACC to parallelize parts of the code that is already running in parallel on multiple cores? I'm not exactly sure exactly what's being asked here. If you're already using multiple CPU cores and you use OpenACC on top of that on the multi-core, you do run the risk of oversubscribing your cores. If the question is, I have something running in parallel on CPU cores and I want to then use OpenACC to parallelize further onto the GPU, you can do that. And I have an example of that in the third week where we'll have OpenMP threads, each owning a separate GPU, and then I'm sending work to the GPU using OpenACC. So that's kind of attempting to show using threading and multiple devices and different programming models kind of in one giant example. Can OpenACC be integrated with CUDA libraries? Absolutely. Go check out that same OpenACC interoperability repository, or wait about 2 weeks and I'll show some examples. But any OpenACC, any CUDA libraries, cuBLAS, cuFFT, cuRAND, all of those can be called with OpenACC. And the main trick around that is this host data directive, which informs the compiler to send the OpenACC arrays into the CUDA. So Python codes, I've already covered this, that currently there's no planned support for Python, but you should check out Numba, N-U-M-B-A, as one way, or there's, if you search also for Anaconda Accelerate, that's a very similar project that is that handles Python. Can it integrate OpenACC with OpenMPI? Yes, you can use OpenACC with any MPI, and particularly by using that host data directive I mentioned, you can even use GPU-aware MPI. And that example, if you search, go back to our courses page, let me find the link there. If you go to the OpenACC course recordings page here and look for the advanced OpenACC course, which we did last spring, there was a specific talk that demonstrated using OpenACC and MPI. Is pgprof free? pgprof is included with the PGI compiler, and so if you have a license to the PGI compiler, then it is included. PGI compiler can be obtained for free using the OpenACC toolkit. Let me switch back to this slide. If you are affiliated with a university. If you're not affiliated with a university, it is there is a cost for the compiler itself. Are there any compilers for Windows or Visual Studio integration? So the PGI compiler does work on Windows, and I have actually used it to build OpenACC codes on Windows. I have not actually used it with Visual Studio, but it does have Visual Studio integration there. Can we use OpenACC in TurboC? I believe TurboC is a compiler, and it does not support OpenACC. I'm using Visual Studio. Do you know if Visual Studio C++ will feature support for OpenACC? Not to my knowledge, but again, the PGI compiler is available for Windows and does integrate with Visual Studio. Any OpenACC comparisons done on K80 versus P100s in terms of performance? I did show some of that data back here, where you can see a fairly large speed up, but again, you really need to double this line to get the full K80 board. Which C++ compilers support OpenACC? The PGI compiler does, the Cray compiler does, the Pascal compiler does, the G++ and the most recent version does, although it is fairly immature at this point. You really would not expect exceptionally high performance with that one just yet. And then there's also a few research compilers. There's OpenARC, OpenUH are two research compilers available. There's also a compiler based on ROSE that's available. And if you're really into high performance computing, you may have heard of the new supercomputer in China that took the top slot on the top 500 list earlier this year, and that machine, its compiler also supports OpenACC on that platform as well. Can I spend some time on vectorizing versus parallelizing? That's actually a great question. So parallelizing is simply taking an operation and making it run in parallel. So that is a fairly generic term. It can be running on threads. It can be running on really anything, but it's taking operation and making it run in parallel. Vectorizing is a subset of parallelizing. Vectorizing parallelizes by running in vector instructions. So what a vector instruction is one single instruction that operates on multiple data elements at the same time. So on modern CPUs, you typically come across SIMD instructions, single instruction, multiple data. And so how a SIMD instruction works is I will load, in the case of SSE, probably 2 double precisions. In the case of AVX, I may load 4 double precision numbers into one register, and then perform the operation on all of those simultaneously. And so that's known as a vector operation, one instruction that operates across all of those data elements at once. So vectorizing is kind of a subset of parallelizing. Now, with OpenACC, we support multiple levels of parallelism. The lowest level is vector, which is, as I described, one instruction operating across multiple data elements at once. all the way up to coarse-grained parallelism. That is what we discussed, the OpenACC gangs, and those are really coarse-grained, completely independent types of parallelism where nothing overlaps, nothing works. There's no synchronization there. So that's the differences, and I'm actually going to spend some time on the 3 different levels of OpenACC parallelism on the next lecture, so I'm going to defer this a little bit, but at the high level, vectorization is a very, very tight-grained parallelism which operates on multiple data elements in one instruction. Parallelizing goes beyond that could be vector parallelism, or it could be running across CPU threads, or it could even be running across multiple devices or multiple nodes. So parallelizing is the more generic term. What does it mean to handle unified memory and hardware and through device? It's asking, does this mean through device drivers? So that's referring back to an earlier question I had, or earlier statement I had about unified memory and Pascal. So let me find that slide. Unified memory and Pascal. Okay. So here we have unified memory. I did make the note that Pascal handles unified memory and hardware. So for all the GPUs prior to Pascal, so this is basically the Kepler and Maxwell GPUs, unified memory was handled completely in software. So what would happen is I would you call a special library call that would allocate a special type of array, and at the beginning of GPU execution, all of my data that was allocated in that way would be moved over to the GPU and operate on the GPU. And then after I'm done executing on the GPU, if the CPU needs the data, it would page fault and bring the data back to the CPU. And then again, the next time I launch a CUDA kernel, it all get moved back to the GPU. In Pascal and beyond, we have added the support to page fault between the GPU and the CPU. So the GPU can move pages on demand. And so when the GPU encounters a page of memory that it does not have locally, it will page fault and migrate that data to the GPU automatically, and vice versa. So it allows a finer grain of only the data that's needed moving. And it also means that now we can oversubscribe, and you can actually have as much memory as you need available to the GPU, and then the GPU will keep resident what it's able to fit. There was a great talk at last year's GTC. If you go to gputechconf.com and search for, I think it's called The Future of Unified Memory. It has a great talk explaining all of this that will go into much more detail than I'd like to go into here. But the main note is that Pascal does enable on-demand page faulting and on-demand migration of data. So that one is answered. Is it possible with OpenACC to concurrently parallelize parts of the code that are running parallel on 40 CPU threads? You can absolutely parallelize across as many CPU threads as are available to you. Is a gang in OpenACC equivalent to a work group in OpenCL? And I will also add to that, it is likewise roughly equivalent to a thread block in CUDA, so yes. It is a coarse-grained organization of independent parts. So if you're an OpenCL programmer, you could think of it as a work group. If you're a CUDA programmer, you could think of it as a thread block. If you're an OpenMP programmer, you can think of it as a thread team, but that is what a gang is. You understand correctly. Do Pascal GPUs owe their better performance and better power consumption on the unified memory? There's actually a lot more to it. Part of the reason we see improved performance is due to the fine-grained movement of data pages, but in fact, most of the performance improvement comes from a significantly higher memory bandwidth and a drastically redesigned computer architecture. So there's actually pretty significant differences. So, no, the improved unified memory is only a small part. How is the number of gangs determined? This is something the compiler is free to choose for itself using its it's understanding of the code and understanding of the hardware. On GPUs, a compiler will typically choose a whole lot of gangs. I think that with the PGI compiler, it will choose up to 1,000 gangs, and then it'll start kind of reusing threads. But really, it can choose as many as it wants. Or, you know, on a CPU, I don't recall if it does 1 gang per CPU core, or if it does 1 gang per CPU socket. I don't recall for sure. But you as the programmer can override that decision. There is a num gangs clause that you can tell the compiler, in this parallel region, only generate 100 gangs, if that's what you'd like. I typically discourage that. I like to let the compiler choose as many gangs as it sees fit, but you do have some control over that. And in the optimization talk next week, I'll talk more about tuning for the number of gangs and things like that.
Okay, let's take probably the last question, and then we will wrap it up.
Yep, I'm looking for a good one here. Does a single parallel loop statement apply to multiple nested loops? I think that's actually a really good question, so I'll end on that one. So we had, let me pull up the code example and we can talk about here. So here is a doubly nested loop. There's the for loop on the outside, the for loop on the inside, and I have a parallel loop. Now, if I only put ACC parallel loop, what I have told the compiler is first, generate parallelism, and second, this next loop is one that is safe to parallelize. Now, a compiler is free to stop there and only parallelize that loop. However, all of the OpenACC compilers I have used actually will do a complex analysis and figure out for itself, hey, by the way, this loop is also one that I can parallelize, and it will go beyond, above and beyond what is required. So the OpenACC does not require that the compilers do that, but all of the compilers I've used do. The best thing to do is always, in my opinion, to put the loop directive on as many loops as are available, and that gives the compiler all the more information to handle that. The rest of these questions we'll take offline and have them ready to answer potentially in future lectures.
Okay. Thanks a lot. Thanks, Jeff, for the great lecture, and thanks everyone for submitting so many questions. There's a lot of questions that we didn't have time to answer. We will try to do it offline, or we will do it during our next lecture. So excuse us if your question hasn't been answered. Again, thanks again for all the questions for attending. The next lecture gonna be on November 2nd, so in a week, same time, 9 a.m. Pacific. So Jeff, do you mind to pulling the slide with the schedule so people will have a reference?
Absolutely.
The slide will also have a link to the recordings. The recordings will be available by Friday this week. With the recording, we'll also post the Q&As. For the Q&A, it might take us a little bit more time because we would need to answer the question that has not been answered yet. If you have anything pending, you still can ask questions through Stack Overflow. That's one of the resources. Also send your questions to the email openacc@nvidia.com. If you have anything license questions or anything regarding the course logistics or technical, it will all work. We will redirect it to the right people. But again, Stack Overflow is a great resource as well. We are also putting together a developer list for OpenACC. So we'll send you the link to that. That's a new forum that you will be able to use to ask any OpenACC questions. And thanks again for your feedback for the polls. Hope that everyone had a great time, and we will see you all next time, next Wednesday.